I wanted to make a video explaining some intriguing work I've done recently on Discovery. To anyone watching who's not familiar with it, Discovery is a computer system that has a lot of different practical applications in natural language processing. Natural language processing, or NLP, is a branch of artificial intelligence that concentrates on a computer's ability to simulate a human's comprehension of language. At its core, Discovery can take practically any English sentence and provide an in-depth analysis of its structure and the words within it. It determines the part of speech of each word as it applies to the sentence, determines, at a minimum, which senses or dictionary definitions apply in sentence context, and diagrams the sentence in a manner not much different from the sentence diagramming we learned in grade school. A more complete explanation of Discovery can be found on my development website, discoverynlp.com. Discovery is unique in that it's not a language model like the more commonly known ChatGPT and Bard, or uses other approaches like statistical analysis. Instead, Discovery is rule-based. Its design avoids the massive problems and controversies surrounding language models, but that's not the focus of this video. Nor is it the various practical applications for which it can be used, nor the different sentence analysis stages at the heart of those applications, nor the organization and maintenance of those rules that it uses. Those would all be topics for other videos, if I ever decided to make them. The focus of this video is a stage called part-of-speech tagging. Despite Discovery's capabilities, this has been the slowest and least efficient stage in its sentence analysis process, its weakest link. That is, it was, until now. That's the intriguing part. So what is part-of-speech tagging? It's the first item I mentioned, the process of tagging or designating a word in a sentence as corresponding to a particular part of speech. In my introductory video, I use an extreme example to clarify. The word well can be an adjective, noun, verb, or regular adverb, depending on its use in a sentence. As any part of speech, this one word has more than one definition beyond those displayed here. So how do you determine the part of speech of each word in a sentence like a well's well? There are 128 possibilities or permutations, but only one applies: adjective, noun, verb, adverb. Conventional approaches to part-of-speech tagging assume that just one set of parts of speech apply to the sentence and have various levels of accuracy. My approach, in contrast, considers all possible permutations and determines which of them resolve to a single grammatical clause. There is no accuracy percentage. In Discovery, there is simply one or more permutations that conform to the rules, most often just one. Nor is there any huge corpus of English text for the system to search for examples. In Discovery, the entire analysis is governed by rules. In the introductory video on my development site, I compare this process to a bank vault. The lock's combination, or rather a permutation of numbers in a particular order of turns, succeeds in opening the vault. The more numbers there are on the knob, and the higher the number of required turns, the more permutations are possible. The sheer number of combinations is enormous. That's the vault's very purpose, to secure its contents and discourage robbers by making the likelihood of finding the right combination practically impossible. Likewise, the more words that a given sentence has, and the more parts of speech each word can be, the higher the number of possible part-of-speech permutations there are that can apply to the sentence. That's where the comparison ends. Unlike words and sentences, the robber has no means of knowing in advance which series of numbers are better at opening the vault than others. So unless the cops are delayed by a long enough line at Dunkin' Donuts, he has no alternative but to exhaustively attempt all possible combinations, which may number in the tens or hundreds of thousands, until he eventually winds up with the right one. Such a task would, of course, require an unreasonable and ridiculous length of time. In contrast, we humans, particularly children with little to no knowledge of grammar, never have to go through that much effort. Human beings don't test every possible part of speech permutation for every sentence we encounter. Quite the opposite. We understand a sentence by recognizing the function of each word in a sentence as quickly as we read or hear it. Solving the problem and making it as efficient as a human might could provide clues as to how we humans do so with practically no effort at all. My goal for the past month, then, was to find as many ways as possible to reduce the number of iterations and steps to the bare minimum necessary and still yield the same results as if all permutations were generated and tested exhaustively. The part-of-speech tagging stage starts after Discovery looks up all the words in a sentence in its vocabulary. When it determines all possible parts of speech, it also designates whether they are identifiers, non-identifiers, or, for lack of a better term for them, hybrids. An identifier, as coined by linguist Charles Fries, is a signal word, one whose definition is not normally ambiguous and serves the purpose of signaling or identifying the functions of other words in the sentence. In Discovery's grammar, these include prepositions, articles, conjunctions, pronouns, auxiliary verbs, and irregular adverbs. In permutations, identifiers are denoted by capital letters and punctuation marks. A non-identifier is a word of any other type which may have more than one part of speech. These are limited to nouns, verbs, adjectives, and regular adverbs. In permutations, non-identifiers are denoted by smaller case letters and numbers. A hybrid is a word that may function as either an identifier or non-identifier. In a sentence, some non-identifiers most often occur in tandem. One or more consecutive non-identifiers are called fragments. For example, the sentence, "The quick brown fox jumps over the lazy dog," has two fragments, "Quick brown fox jumps" and "lazy dog." There is also a means and system to exclude certain types of fragments that occur between a pair of identifiers. For example, desires can be a verb and noun, but is only regarded as a noun if it follows an article like the. A peculiar problem arises when hybrids are used. In the same sentence, over can not only be a preposition, but also a noun, an adjective, or a regular adverb. There is no definite demarcation whether these words are within a fragment or follow or precede it. To solve this problem, I built a programming object called a triad to enable the system to represent hybrids as either identifiers or non-identifiers, as shown in this example. Depending on how a sentence is worded, the triads that represent a sentence can consist of any combination of an initial identifier, a non-identifier fragment, and/or an ending identifier. The triads that Discovery generates for a sentence are in a particular order. To keep track of them, each triad is designated with a letter, the first with A, the second with B, the third with C, and so on. This technique ensures that Discovery can generate all possible permutations to test for a sentence, even if it does contain hybrids. From there, Discovery executes rules on permutations in an attempt to deduce whether they can resolve to a single grammatical clause, which is designated by a smaller case letter C. Whatever the case, the result is an abbreviation. In some cases, abbreviations indicate which permutations are those which are closest to being the ones that apply to the entire sentence. Those that are judged to be better are retained, and those that aren't are discarded. In this process, at various points, words from the first few triads from left to right, called partial permutations, are tested. At each iteration, some are retained, some are discarded, and those that remain add words from the next set of triads, and those are tested. The process repeats until all remaining triads for the entire sentence are tested. At that end point, all final permutations that resolve to a single clause are retained, and all others are discarded. From there, the next stage of sentence analysis continues. This process has helped to prevent exhaustively generating and testing all permutations, vastly reducing the number in order to accelerate processing. Still, after re-examining it a month ago, I saw in many different ways that even this was often inefficient. No matter that some sentences in a 19-sentence test processed more quickly than others. The longer the sentences, the longer the processing time. Waiting around for sentences to process would aggravate users. In the worst case was one sentence in the test, which is 29 words long, and would have otherwise generated and tested a whopping 294,912 permutations. That sentence failed. It exhausted all my PC's resources, locked up, and never finished the job. So I looked for various ways to speed up the part-of-speech tagging process. First, in problems of this type, coders face the decision of whether to use one of two algorithms, a breadth-first search or a depth-first search. A breadth-first search traverses a point in a tree or hierarchy and visits all points adjacent to that point, then moves to the next level of adjacent points and repeats the process. In contrast, a depth-first search begins at a topmost point or root of a tree or hierarchy and traverses toward the end of each branch, then backtracks to the nearest point and traverses toward the end of that branch, and so on. Depending on the nature of the programming problem, either algorithm traverses all points in the tree until the entire tree is analyzed, just in different ways. But the fact that some words can be either identifiers or non-identifiers presents a problem of which algorithm to choose to solve the problem. A breadth-first search can't be used because with the presence of hybrids in the sentence, there may be no identifiable adjacent levels. A depth-first search can't be used because that would generate the exhaustive list of permutations that I want to avoid. The solution to this particular problem, however, was to use both. Some coders may understandably insist on only one or the other, and that it's impossible to use both. But it isn't impossible. I used a depth-first search to generate all triad sequences and organize them according to the number of words in the sentence they represented. Then, based on that order, used those as levels in a breadth-first search. This allowed Discovery to discard partial permutations that didn't apply much more quickly. That's not all. I created a database table defined to list abbreviation for sentences that did not result in final permutations resolving to a single clause. That inhibited the processing of sentences where the abbreviations did work, so I included an additional field to detect exceptions, so that when an abbreviation in this table was encountered which was designated as an exception, the partial permutation was retained and the processing continued without interruption. To prevent rules from being repeatedly executed for the same words, I inserted abbreviations from partial permutations into subsequent partial permutations and started execution of rules only from those points. I also eliminated certain part-of-speech letters which do not affect analysis and included them only in final permutations. I also eliminated the formation of triad sequences that have no permutations to test so that they're never created in the first place. Lastly, in partial permutations, I prevented the execution of rules involving one part-of-speech letter, which is unnecessary when the abbreviation is identical. The results of all these measures has been astounding. What was once the slowest and least efficient stage in Discovery sentence analysis is now the fastest and most efficient. 15 sentences out of the 19 in the test execute part-speech tagging in less than half a second. And the worst-case sentence, which previously never processed at all, executed this stage in 3.12 seconds, roughly twice as fast as a human can read it. Beyond that, I could probably start the analysis from the point that the user begins entering in this sentence and continue in it during the brief span of time that the user types it. But since I have so many other things to work on, I'm going to hold off on that for another time. Fantastic, huh?